Hello grade 10s, welcome to my channel and welcome to also this video where we're going to be looking at your roughly entire syllabus for grade 10 for physical science paper 2, which is chemistry. Okay, I've been doing a lot of work for grade 12s, which I think has gone on fairly successfully. So I figured it is also important to shed a bit of light in your direction as well, so that you also can benefit from a bit of what I am capable of showing. Otherwise, guys, I cannot ever emphasize the importance of studying. Okay, don't be happy relaxing, actually start studying more than you relax. Okay, so let's do this one, guys. Let's capture you with chemistry starting from November 2022. As you could see, this paper was from the EC, probably the final for last year. Okay, so let's see. It's a 2-hour paper, so this can take a while. I've already highlighted some of the best instructions that I suppose you should look at. Well, 8 says you're advised to use the data sheets. It's important because the most important part of those data sheets is going to be essentially for chemistry is the periodic table. Okay, the periodic table is your friend there. The rest, you decide when you use or when you need it and when you don't. Okay, it says now show all formulae and substitutions. As you know, in physics, this is most likely the areas where you're getting marks, and then you're rounding off of the final answers. It's a minimum of 2 decimal places, which is 2 or more decimals, okay, are acceptable, and then you can't write less than 2 decimals. And then 11 says give brief explanations, motivations, etc. This is my favorite part. Okay, it means absolutely anything that is acceptable and scientific and does not distort the essence of the scientific knowledge or phenomenon being described. Okay, let's jump into these questions. Also make sure you read the local instructions, but it's nothing really out of the ordinary. Now let's get to 1.1. It says which one of the following is a mixture? Okay, what do you understand, guys, by a mixture? Basically, a mixture says there is no chemical bonding. There is no chemical bonding, okay, between atoms of the substances. Okay, it can be the atoms of the substance or the substances, it doesn't matter. What matters is that there is no chemical bonding. And then of course, what do I mean? It means there's no covalent bonding. Okay, there is no ionic bonding, and then there is no metallic bonding. Okay, those are the 3 types of chemical bonding that actually result into the so-called a chemical change. Okay, so when there's going to be a chemical change, it means either one of these 3 types of bonding have taken place. But intermolecular forces means it's just that particles or molecules of a substance or a compound attract each other because of their polarity, not necessarily because of an actual chemical bonding that has taken place. So that means if it is a mixture, we can easily separate them than it would be the case when we're trying to break the bonds. Okay, so again, guys, this is a concept that in grade 10 it is very important to make sure you understand and also know the different types of mixtures. Okay, you will see as you progress with your lessons. Now we're told here which one of the following is a mixture. What about diamond? Diamond is basically a pure substance, isn't it? A mixture is what would be impure. This is a pure substance because all the atoms involved here are of the same element. Okay, so that is a pure substance. It's not a mixture. Distilled water is again a pure substance. It's not an impure substance, so it's not a mixture. Okay, vinegar. What do we know about vinegar? Well, we know that vinegar is a mixture of water plus acetic acid, or the more scientific name, you can say ethanoic acid. And then of course you may have some flavorings. Okay, just to give it a bit of an appealing, perhaps, smell or odor. Okay, now that is definitely a mixture. We understand that. And then if we're looking at sodium chloride, sodium is a metal, and then chlorine is a halogen, which is a non-metal. So we know that between these two there is an electron transfer. So we know that they form an ionic bond. Okay, now we know that sodium has a lower electronegativity compared to chlorine, so sodium would rather shed electrons and chlorine would rather accept electrons to assume a very stable electronic structure. Okay, so because this is forming a bond, there is essentially a chemical change here. So this then results in a pure substance of some kind. Okay, so this becomes a pure substance, not a mixture, because there is a chemical change. Here there is no chemical change, but of course this is what you would call a homogeneous mixture, because everything becomes almost like liquid. Okay, so what is the answer here? Is C. Okay, so I hope you can understand why. So I'm just trying to revise a few ideas to assist you to learn. Okay, the heating curve, again, this is another important concept in chemistry, especially for grade 10s, because it is highly experimental in nature, and it essentially explains a whole lot of chemical change that you'll come across and the understanding thereof as to why it happens. Okay, so this heating curve is not drawn to scale of a compound shown below. Okay, so now again, what is the measure of the temperature? There is important. It can be kelvins, it can be the degrees Celsius scale, so not a problem. Now there are two important areas to observe in a chemical change. It is the lower fixed point and the higher fixed point, or the upper fixed point, in the ranges of the temperatures. Okay, so now when we're looking at the lower fixed point, okay, it really coincides with what we call the freezing point. I'll just write FP, and or melting point, because this is when a substance actually freezes or melts. Okay, so it's either freezing point or melting point. That would be the lower portion of the scale. And then how do you see that? You see it with this horizontal line, where the temperature during a portion of time in that particular level of temperature is actually constant. And then of course we know that we have also an upper fixed point. Okay, this upper fixed point basically corresponds to the boiling point. I'll just write BP. Okay, that's great. So what do we understand about these 2 points? Well, what we understand about them is the fact that these 2 points result in the so-called phase change. Okay, so there is a phase change when you are seeing these 2 points. Okay, again, this one is a horizontal point, but maybe let's give it its own color. Okay, so you can see that up until point D, there's also that horizontal format. So what does this mean? Basically, it means a substance is changing phase. For example, if you take ice and then you put it in a container or a glass beaker and then you heat it gently with a Bunsen flame there, what happens is, as the ice melts into liquid, you will notice that the temperature of the thermometer does not change, okay, for a while. Okay, so that is the melting point. So basically it's melting here. Okay, that is the lower level. And then now you will see that there is actually a gentle rise of temperature at some point in between. Okay, so what is happening there? Well, we know that, okay, the only understanding we can gather is that when the temperature remains constant, it means the heating or the energy, the heat energy that we're transferring into the substance is essentially just separating the molecules of the substance. Now we're expending that energy, separating the molecules, so it is dissipated that way, rather than to increase the kinetic energy of the actual particles. That's when we see that their kinetic energy remains constant. But then once we complete that phase change, now the molecules are in the same phase now, in the liquid phase. If we're saying melting, this means we're coming from a solid, isn't it? We're coming from a solid. Okay, something is not right here. Doch. We're coming from a solid. Okay? And then now, when the temperature rises, remember, once the temperature of a heated substance actually rises, we know that the temperature gently rises in a particular phase. Okay, but during phase change the temperature does not rise. But once we complete the phase change into another phase, then the temperature can rise. This is actually when we are now energizing the molecules of a substance. So their kinetic energy, their average kinetic energy increases, and then they start moving and moving and moving. But then if these movements become too great, what happens is we hit this top level, which is what we would call the boiling point. Okay, so now this is the boiling point. So this is where the BP is. Okay, again, you will notice that when you're heating that ice to a temperature of 100 degrees, what happens is the liquid boils, and as it boils, you'll notice that the temperature does not change for a while until a particular time when now everything has changed into a gas, or mostly a gas than liquid. And then now as you are heating those gas molecules, then it starts raising the pressure. So if you were boiling water in a closed container, what happens is once you go beyond the boiling point, you will see the lid coming off or popping off because of the rising pressure of the gas molecules, isn't it? So this is basically the essence of the heating curve. So you want to understand this, that once the temperature rises of a heated substance, it means you are in a particular phase already. But once the temperature stays constant when you're heating a substance, it means there is a phase change in that period of time. Okay, guys, now let's try to answer the questions. Now this question says, what would be the physical state of the substance at 100 degrees Celsius? And you can see that 100 degrees Celsius is in between 300 and 400. So this is when this is in a liquid. So this state is liquid. Okay, it's a liquid. All right, because once it starts boiling, it becomes a gas, isn't it? it transforms from a liquid to a gas. What am I writing? Yeah, gas. Okay, so we know that, okay, this becomes a liquid because this is the temperature between the boiling point and the melting point, or you can say the freezing point. So these are questions you cannot guess, guys. You need to make sure knowledge is stored somewhere, okay? So you can't guess. So the answer becomes B. So the reason why it's not a solid, because it's a solid below its melting point or freezing point. At or below, it becomes more or less solid, and then it becomes liquid between the two extremes of temperatures or ranges of temperatures. It becomes a gas beyond the boiling point, okay? So it becomes a gas at and more than the boiling point. So the answer is 100 is not the boiling point of the substance. And then it changes from solid to liquid when it melts. So it's a melting point that corresponds with the lower fixed point on the temperature chart there. So that is why those ones are not the answers. Okay, guys, I know I'm taking a bit of time to explain, but let's just continue. Now 1.3 says, what did we choose there? Yeah, B, liquid. Okay. 1.3 says the atom X, okay, of an element of group 17, but we normally use this one. So remember, group 7 sometimes it's called group 17, but this one really freaks me out. But it's okay, you probably are already accustomed with those signatures of groups. Okay, now it ionizes, okay, to become, look at that, it becomes an N ion, okay, which is a negatively charged ion. Now what happens when you take a ground state atom? So let's say this is our atom X. Basically this happens when we add an electron, therefore it becomes an N ion, okay, because in its ground state we know that the number of electrons equals the number of protons, meaning it's electrically neutral. But now for it to be negatively charged, we must have added an excess of electrons to that atom. So for this one to be a 1 minus, we must have added a single electron. And you can see here that, okay, usually when you add an electron here, there becomes a release of energy. So basically this is an exothermic process. Okay, it releases energy. So whenever you add an electron to an atom, there's an energy release, and we call that electron affinity for some reason, some weird reason that I don't know. Okay, not a problem. Anyway, so now the question says the mass number of X increases. The mass number, does it really increase? The answer is a hell no. Okay, why do I know that? Because I know the mass number, we normally use the letter U, is given by the number of neutrons, which is N, plus the number of protons, which is P. Okay, so this is the number of protons, which is positive charges. The neutrons are basically, you can just say non-charged. Okay, so now what have we done here? We only added an electron, so we did not tamper with these, because these two are concentrated in the nucleus of an atom. Okay, they make up the nucleus of an atom. So experiments of old have shown clearly that the mass number is determined by these two, the number of protons and the number of neutrons, and this is heavily concreted at the nucleus of an atom. All right, so basically we know that an electron is too light. It's basically a wave of energy than a recognizable mass. So you will have to have a lot of electrons before you can actually significantly add a mass, because even a mole is so light that it's almost unnoticeable. Okay, so that means the mass number was not tampered with, because in this equation there's no electrons. So adding an electron does not change the atomic mass or the mass number. So that's why I know it does not increase. Then what about the atomic number? The atomic number, does it really decrease? The answer is no. Okay, again, what is the atomic number? You will know that it's the letter Z. The atomic number basically is equal to the number of protons. Okay, only. That is what it means. But we sometimes use the atomic number to know the number of electrons in a neutral atom, because when it is electrically neutral, it means the number of positively charged subatomic particles is equal to the number of negatively charged subatomic particles. So it's an inference that the number of electrons is also given by the atomic number. But technically, by definition, the atomic number is equal to the number of protons in an element. Again, you don't see negative charges, so we only added an electron. We did not tamper with the number of protons. So that's why the atomic number stays the same. It does not change. So that's why it cannot be decreasing as a result. So the number of electrons decreases? No, because we can tell that from our equation here, we are adding an electron. So it's not decreasing, but it's definitely increasing. So the answer here becomes D. Okay guys, this is very important. Please make sure you understand these things. All right, 1.4 says the molecular formula. Okay, again, you will be introduced to terms like this of a certain carbon compound. So you see there's carbon, hydrogen, and oxygen. And then of course, if you see something like this and you are in grade 12, you know that you're looking at possibly either an ester or you're looking at an carboxylic acid. Okay, but don't worry about what exactly are you looking at. For you, just focus on the molecular formula. Okay, now it says which one of the following can be the empirical formula, okay, of this compound. Now we need to know the difference between molecular versus empirical formula. So what is a molecular formula? The molecular formula is the exact whole number ratio of atoms. I cannot find space. Is the exact whole number ratio of atoms in a molecule. Okay, maybe let's continue here. In a molecule or compound. Okay. So that is how you define a molecular formula. But what would be an empirical formula, therefore? This one is the simplest, okay, simplest whole number ratio of atoms in a molecule. Okay, not molecules. In a molecule or compound. Okay, so this one is the simplest. If you were to think of a half versus 4/8, right? 4/8 is equivalent to a half, but this is the simplest versus this one. Okay, so this would be a molecular formula, this would be an empirical formula. This is just to draw analogy between those two. So these ones are actually equivalent but not equal. Sometimes always make a mess of not really being clear as to when you talk of equivalence versus equality. So equivalence means they can result into the simplest same answer, but they're not exactly, proportionally the same, but the ratio itself can be simplified into the same thing. Okay, so that is the most important. So now how do you determine the empirical formula from a molecular formula? You basically take the molecular formula. So this is C4H10O2. And then you're like, okay, these are the molar ratios, isn't it? Then you divide by the smallest in each atom. Okay, the 2 takes the 2 there, the 2 takes 10 to 5, the 2 takes 4 to 2. And then what is the result? The resulting molar ratio here, the simplest is C2H5. Oh, so can you see, you can't guess this thing, you have to determine it. So this one is C2H5O, so C becomes the answer. Again, these are one of those questions you can't just look at them and guess an answer. You need to understand the question and also understand what procedures must you perform to answer the question. Okay, so please guys pay attention. Now let's look at 1.5. So 1.5, and I can tell you this is also relevant up until grade 12. You know, grade 12 of 2022, in their organic chemistry section, they had a question related to this, but it was more complex than just determining the molecular formula. In fact, they were given an empirical formula and then they had to convert that to a molecular formula, and from that molecular formula, by knowing the the structure of that compound in terms of the structural formula, this is when you can actually learn now what substances were used, because yeah, that question was a bit silly, but it was a good question. Okay, 1.5 says, which one of the following elements has the highest ionization energy? Now basically, what is ionization energy, guys? Now simply put, ionization energy, if you take element X and then you add heat, for example, you will be able to take out an electron in the outer energy structure, so you end up with a positive ion, right? Now of course we're releasing an electron, so that is what is happening. So you can see this one is the opposite of forming an anion, right? So you can say it's the minimum energy required to remove an electron from a ground state of an atom or a gas, and to form a positive ion. So the result of this thing is to form a positive ion of that atom or element. Okay, great. But the key is the energy needed you are adding. So you can see that this is an endothermic process. Okay, it requires energy. Great. So now ionization energy. Okay, the question is now, which one is it potassium, is it lithium, is it cesium, is it sodium? But of note is that these are all elements of group 1. I know them by heart. Okay, because I have a lot of experience with the periodic table, but you may have a bit of a challenge because you're still shaky about it. But if you learn it to know it best, you should not be struggling here. Now we have to decide now, how do we decide which one has the highest? Basically, the ionization energy is related to the radius of an atom. Okay, because for us to know how much energy we need, we have to think about the radius of an atom. For example, if you would have a nucleus there, and then we have this circle right there. Let's say now we have an orbiting electron here. It's an orbiting electron, and you know that at the center we've got a proton, right? Protons are in the nucleus. Now you can see that between these two there's an electrostatic force, okay, of attraction, because unlike charges attract each other. So that means for one to break free this electron, of course assuming that this is an outer energy level, to then break free this electron, you'll have to break this electrostatic force, okay, basically. But if you've got a center there, and then you've got this atom over there, again you still have a positive charge, which is protons, and then you've got this orbiting electron in its outer energy structure. But do you see now this electrostatic force is over a longer distance? So if you guys learned something about Coulomb's law. You will know that the electrostatic force between 2 point charges is inversely proportional to the square of the distance between them. So the bigger the distance, the lesser is the electrostatic force. So you can see it's easier to take this guy away because it's far away from what is guarding it. This one is too close. To take this one takes effort, isn't it? Even to steal when the owner is around, it's more difficult than when the owner is away. So think of those things when you are dealing with these kinds of problems. But again, well, if you study the periodic table, you will have some understanding about the radii of those atoms. But of importance basically here is that ionization energy is related to what we call electron affinity. Okay, basically if you define this is the energy released when an electron is added to an atom. So meaning these atoms have a tendency to attract electrons, and then of course the tendency to gobble electrons is what we call electronegativity, the measure we use the electronegativity. Okay, so now practically in the periodic table we have this. We've got this guy, the electronegativity, but this one you may not have because it's some experimental measure. So if they didn't volunteer it for you, it's almost difficult to just calculate it without performing some sort of an experiment. Okay, great stuff. So now what do we know? The higher the electronegativity, the higher is the electron affinity. Okay, and the higher is the ionization energy needed to strip an electron free from that. And then of course the higher the electronegativity, the lower is the radius of that atom. So meaning the smaller radius has a higher electronegativity, a high electron affinity, and a high ionization energy to form a positive ion. Okay guys, so now we need to look at this one. Since we know these are elements of group 1, we're just going to go into our periodic table and look for which one of these ones that they've given us. So I'm sorry guys for this parade. It's very difficult. As I said, the radius, if this line here represents the radii, so we know that the radius increases down the group, okay, while electronegativity increases up the group. All right, great stuff. And then what also do we know? The groups are the columns, right? And then now across periods, the periods are the rows. Across the rows, we know that the radius decreases. Okay, of course there are some exceptions. There are some exceptions to this rule, so be careful of using that. But I think if we use the electronegativity, it makes life easy. Again, if we're using the groups, it becomes easy. So we know that we're given the lithium, we're given sodium, we're given potassium, we're given cesium. As you can see, the one that has the smallest radius, if we're following the pattern that we drew, is lithium. Again, if you're looking at the electronegativity, you can see it's smallest from the bottom and it's higher at the top. So lithium has the higher electronegativity. So that means our answer to that question is lithium. Okay guys, so remember such things. Again, know your way around the periodic table. It's critical. It is critical. Okay, let's try guys to end this pain quickly of MCQs. Let's quickly do this and finish. So here we can see that, okay, the answer becomes lithium because it is the most electronegative of these substances given here, and of course it has a smaller radius to then give us what we have worked through. So do you see the pieces of information that you need to understand? So these are some of the questions that are essentially very tricky, but at the same time, if you possess a bit of that basic knowledge, they're not too complicated. Okay, 1.6 says which one of the following statements is correct? 1 mole is equal to, is it 44 grams of carbon dioxide? Again, how do we know the number of moles? It is the mass over the molar mass, okay? Small letter m over capital letter M. So that is what you need to remember. Now let's look at the number of moles of carbon dioxide. The number of moles is going to be mass, which is 44 over molar mass. The molar mass we determine by using the atomic mass in the periodic table. That of carbon is 12, plus, once you see a subscript, you're doubling it, so it's 16 times 2. Okay, so this is basically 44 over, this is 32 plus 12, which is 44. That is equal to 1 mole, okay? Because this is grams per mole, this is grams. Grams cancel out per mole, the mole becomes the numerator. So you know how these things are done, right? Great. So again, let's look at the number of moles of oxygen. 32 grams over the molar mass is going to be atomic mass multiplied by 2, because that is a diatomic molecule. So this is 32 over 32, which is essentially 1 mole. Okay, again we can see that these two essentially give us 1 mole of a substance. Let's look at the nitrogen. It's going to be 14, the mass that we're given. The mass must be in grams, by the way. And then this one, the elemental mass is 14, but now we're doubling it because it's a diatomic molecule. So this is 14 over 28, which is 0.5 mole. Okay, so that is not equal to 1 mole. All right, so you can already see here the answer is B. Okay, it's 1 and 2. All right, guys, so that is again one of those indirect questions which you cannot guess the answer. You have to work it out. You have to work it out. Okay, 1.7 says consider the off-bar diagram. So what is the off-bar? Basically, this is not a person's name. Okay, this is not the name of a person, but it's a German term or German word. It's the German word for building up. Okay, you're building up from the ground. Okay, so that is what we know. This represents the electronic structure of an atom. Okay, great. So you can see here the bottom is the lowest energy level, so sorry, it corresponds with the 1s, and then the second energy level is basically 1s and 2p. Okay, so this is one and the same thing. These ones, they add up to the second energy level. Okay, this is the first energy level. This is the first, this is the second energy level. Okay, let's just say E level. Okay, and then of course the third energy level, there's something missing here. The p orbital is also a part of this one. Okay, the p orbital would be a 3p. Okay, it's missing. And then of course this corresponds with the third energy level. Okay, so this, okay, let's use the other color. Okay, these two make up what we call the third energy level. the third E level. Let's just say E level. Okay, great stuff. Okay guys, I'm wasting time now. I should be actually done with this, but let's just go up to 45 minutes at least. I mean, you need to understand, right? Right. And then, okay, of an element. Okay, now what do we learn from the off-bow diagram? We can actually find the total number of electrons. Okay, that is what we can learn from this diagram. The total number of electrons. How many are they? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So they are 12. Okay. So the total number of an electron, because they said it's an element, so we'll assume that it's in ground state. This corresponds with what we call the atomic number, therefore. Atomic number, which is denoted by the letter Z. Okay, this is if we know this is an element, but if they said it's an ion, it's a different story. Okay, the number of electrons don't give us the atomic number. Great, that is number one. So that means the atomic number can help us identify this element, because in the periodic table they are listed according to the atomic numbers. Okay, but now what does the atomic number also tell us about number of protons, which are positive charges, isn't it? Because the number of protons actually defines the number of electrons. It gives us the atomic number essentially. But provided you are not told this is an ion. Okay, these are the pieces of information you want to piece together when you work out diagrams like this. Okay, that is point number one. What can be learned again? What point can we add to this? If you think about it, what is the outer energy level here? It is the third, because we can see that the electrons are in the third. So this becomes the outermost energy level. The third energy level here is the outermost energy level. Okay, and electrons in the outermost energy level, they tell us what? The valence electrons. Okay, so valence electrons here, how many are they? The outermost energy level is the third here. There's only 2. So those are the 2 valence electrons. And then if we've got 2 valence electrons, what can we learn from that? This gives us the group number. So if it is of valency 2, then it means the element belongs to group 2. Remember, groups are the columns. So this can also help you to identify this element. You look for an element of group 2 that has the atomic number 12. So this can help you to identify this. Okay, now the other thing, the outermost energy level, in fact this would be the third bullet actually. The outermost energy level, which is the third, gives us the period in which this element is found. And you know that the period talks about the row, okay, in which row, horizontally. So when you take the group number and the row number, the period number, you can actually identify this element even without knowing its atomic number. Okay, so this helps to work out the identity of that element and a lot more, to also understand its behavior. You can see here there's too many empty spaces, so this element is more likely to lose these valence electrons. Okay, it's more likely to lose these valence electrons than to gain electrons, because it's just a deficit too great to bridge, isn't it? So now we know that this is an element of group 2. Now I told you the element is A or N. Is it a halogen? No, halogens are elements of group 7. So a bit of theory there is important, guys. We call them halogens, and then they are negative ions, or N ions, are called halides. And then noble gases, these are elements of group 8. Okay, they are called noble gases because they are chemically inert. Okay, we call them inert gases. So no. Is it an alkali metal? When you say an alkali metal, you're talking about elements of group 1. We call them alkali metals. And then alkaline earth metals are essentially elements of group 2. That is a bit of theory that you need to know. And that ticks the box. So that is the final answer there. Okay. I know, guys, we've taken about 45 minutes to answer a simple question like this, but I felt the necessity to give a bit of the groundwork to assist you to understand, your grade 10 chemistry, which is, very difficult, because at first this is when you're starting to get introduced into some chemical formulas and chemical stuffs that looks like highly fictitious. It's like fiction, isn't it? So it's very difficult to believe. Yeah, something like that. So libali. Now we don't want to let you not believe. So the most important is to work using the tool, the periodic table, and to make sure you study those areas that I highlighted. But above all, you have to make sure you understand the periodic table. Okay, I've highlighted some of the most important areas. Okay, let's answer this question too. The graph below shows a heating curve. Again, do you see, guys, it's coming back. So if you messed up that MCQ question on the heating curve, you may resurrect yourself here, and in fact this can help you to remember some of the things, then you can go correct them. But if you didn't know it all, then this one is already fluffed. Okay, trust me. Okay, now this is the graph, shows a heating curve of a pure substance, okay, under standard conditions. Why do we have to emphasize the pure? Because when you're heating an impure substance, you are doing something called fractional distillation. This is when you are actually separating this, because one is going to evaporate because it reaches perhaps its boiling point before the other one. This is how you separate sort of like homogeneous homogeneous substances, or even heterogeneous substances. You can do that. But yeah, that is just something else. So now this is trying to tell that this heating has nothing to do with separating, components of this substance, but we're just trying to play with the physical change, which also plays the basis for a chemical change. All right, let us study our diagram here. So we're given the measure of the degree scale. So it's the degree Celsius. Okay, easy. And then of course we're looking for our friends here. The horizontal friends, they kind of give us a bit of an intel as to where we are. The lowest fixed point as you head above. Okay, I'm not going to repeat most of the things now. The lowest fixed, this is the freezing point or the melting point. Okay, that is where we are. And then the upper fixed, you see these by these horizontal lines, or the temperature remaining constant. And then of course the upper, okay, let's use a different color. The upper fixed point corresponds with the boiling point. And the key to these ranges here is that there is a chemical change at them. Sorry, a phase change. That is very important to remember. Okay, and you already had the explanation why there is a phase change here. But then let's see, what are these rising areas? Let's use this gold. Now you see that there's this portion where there is a rise in the temperature. There's that portion, there's a rise in the temperature, and then there's that portion, there's a rise in the temperature. So what is going on in those areas where everything seems to be rising? Well, we know that if we're saying this is the freezing point, okay, the freezing point, it means here, when there's a change in temperature, that means we're in the same phase. So this is basically a solid phase, okay? That's what it is. Because when you're heating a solid, remember, there's what you call molecules. They just simply vibrate. They don't really move far apart. They are vibrating in a fixed position. Because once it's in a solid, then the positions of the molecules are fixed. As you know that in a crystal lattice. The positions of those, say, particles or molecules are fixed. Okay, that's fine. So this means we're just heating a solid here. But once we reach this temperature, because it will rise and rise and rise, because these become more vibrating, and then as they do so, we reach a point whereby now the fixed positions are lost, so they start to move a bit. That means we're becoming more fluid, right? They start to become more mobile, okay? You know that ions move a bit more in a liquid than in a solid, okay? Now, why is this temperature so constant then? It means we are changing phase here from solid to liquid, because now the energy that we are adding here is being used up in separating the molecules to make up the liquid from a solid. That's why there is no rise, because we're actually expanding that heat. We're not, retaining it. But once all of this solid is a liquid, so this is the melting process. So we're melting here. Okay? Now once everything is liquid, then we start to change, because now any more additional heat will actually increase the kinetic energy, the average kinetic energy of the particles or the molecules in this substance. This is when you see a rise. So that means we are in another phase. So this is liquid. Okay? Of course, negative temperatures associated with frozen states or ice. Okay? So that's why I'm talking about liquid right now, but my liquid looks horrible. Liquid, okay? So that liquid goes on, and then once we hit the topmost point, then we know that we start boiling here. Okay? Again, we're changing a phase from now liquid to gas, all right? That's what happens. And as you see, when liquid is starting to boil, the thermometer that you put in, you will see that it doesn't change the temperature for a few moments. But after a certain period of time, it starts changing, okay? Because now we are heating a gas, okay? Here we are heating a gas, and now when we heat a gas, what happens? The gas particles are far apart, so they move a lot. And what happens? When you heat a gas, you're raising the pressure. And pressure is directly proportional to temperature, isn't it? And what happens when pressure rises? The lid comes off. If the lid was on, okay, it comes off, okay, because now the gas particles keep knocking the walls of the container, and they are raising the pressure, and then the lid will eventually come off. So guys, you need to make sure you understand these things, okay? Again, we said in a gas, the molecules are far apart. There's almost no intermolecular forces between them. In liquid, they exist, but they're weaker than in a solid state. Okay, not a problem. So that is what we can gather here. Now we're told to define the temperature. Now from your lower grades, you know that when they ask you what is the temperature, temperature is how hot or cold a substance is. But now you are doing grade 10. You cannot say that. You need to tell us what is temperature. Temperature is defined as the measure or a measure of the average kinetic energy of particles, or can say molecules, of a substance, because it's actually the molecules that are moving. Okay, so basically it is a measure of the average kinetic energy. So key word is that it's average, it's not actual, it's the average. Okay, molecules of a substance. Great, that is most important. Easy 2 marks there. So nothing really major. 2.2. What can we say here? What is the boiling point of this particular substance? Now we know that it is the uppermost fixed point, which is 30 degrees Celsius. Okay, so now we know we can answer this one nicely. This one is taken from the graph. Make a habit of writing the units, because if you don't write them, you lose marks, guys. 2.3. Now it says, during which time intervals? We're looking at time interval or time intervals. Will the forces of attraction. Now forces of attraction is what we call van der Waals forces, or aka intermolecular forces. Intermolecular forces, not intramolecular forces. So these ones are not bonding per se, although we talk of the strongest as hydrogen bonding, but it's a misnomer. It's not exactly a bond, okay, because there's no sharing of electrons per se, but it just tells us about the measure of the polarity of that substance. Okay, so these are what binds molecules together. So let's say we have an oxygen atom right there, and then we've got a hydrogen atom attached, and then hydrogen atom attached, and you know that is a water molecule, right? This side is partially negative, isn't it? While this end is partially, we use the sigma, positive, isn't it? Great. Now if you bring in another molecule here, another water molecule here, and then of course you've got those hydrogens there. Okay, maybe let's change the conformation a bit to make it work. So this one is going to be hydrogens this side and that side. So we know that this side is negative, and then this side is partially positive. Oh, sometimes I don't know how to show these ones. Okay, now remember, because there's two different charges here involved, okay, so these ones will attract each other so that these two molecules are closer together. So you can see now that, okay, if the distance is shorter, they are closer together. But if this water molecule here is here, and then its hydrogens are there, and then this one is partially positive with this side. Why is my sigma looking strange now? This one is partially negative, in fact strongly negative, because it's a polar substance. And then the other water molecule is over there. Okay, all right, so it's over there, and then those are the hydrogens right there, and then that is partially positive, that is somewhat negative. So do you see the intermolecular forces are acting over a very long distance between the two molecules? So usually this one is going to be a lot stronger than it is the case. So this is what would be a liquid phase, this is what would be a gaseous phase, and then if it becomes a lot more smaller and fixed, then it becomes a solid. So think of this analogy as your answer. So now I told you at which time interval or intervals will the forces of attraction, the intermolecular forces, not the bonding forces, between the particles be at their weakest. They are at their weakest in the gaseous phase because the molecules are far apart. So when we were heating a gas here, we're heating a gas between 30 and 40 because there was a rise in temperature. Here we were just, transitioning between liquid to gas, okay? So they are at the weakest when they are in a gas because the gas particles are far apart. There's almost no intermolecular forces between them than a liquid and a solid. So to answer 2.3.1, we know that 30 to 40 minutes, because we're talking about time intervals this time around. So you can see this was hitting a gas. Gas particles are far apart, so the intermolecular forces are the weakest at that time. All right, again, we're hitting it even, so we're making them even more far apart. So they are even the weakest instead of just weak, okay? 2.3.2. Okay, guys, time is trying to run away from me. So now, at which time interval or intervals will the particles vibrate in their fixed positions? So once you hear that word vibrate, okay, and talking about fixed positions, we are talking about a solid or what we call a crystal. That is, because the positions of those particles or molecules are fixed, okay? They don't move around, so they only vibrate in the same position until we overcome that force, okay? Now, when were we heating a solid? Here, between this temperature to that temperature, and that is between 0 and 5 minutes. So that is 0 and 5 minutes. Okay, great stuff. So there we are. And then the next one says the average kinetic energy, hear that, of the particles remains the same, meaning it's constant. Now you're looking at those areas there and there. So this is 5 to 10 and 20 to 30 minutes. So this is 2.3.3. So this was 5 to 10 minutes and 20 to 30 minutes. Okay, easy stuff. So you can see those ones, nice and easy. Now it says give a reason for your answer in 2.2.3. So I have been singing it all along. So you know that why is the temperature constant? Because there's a phase change. And why? Because we're separating the molecules a little bit more. So now to answer 2.3.4, we can say the added heat energy is used to separate the molecules, okay, of the substance. Hence, okay, maybe hence their average kinetic energy does not change. Okay, of course we can see that the temperature is constant, and so the temperature is constant, and so the temperature remains constant. Bese nibhala kahle ndazi sekuphinde kwathi bese nibhala ngconywana ne, but yandazi mos bantu njani. Okay, what is important is that you are explaining where did the heat go. The heat went into separating the molecules because you need a bit of heat to overcome those intermolecular forces, and therefore that means the average kinetic energy is not being increased at that state. That's why the temperature stays constant. But as soon as you've overcome, that level of the intermolecular forces into the other phase, then this one becomes maintained for some time as the temperature increases. Okay, great stuff. So this is how you do that. So if you explain where that heat went, it went into separating the molecules. That's key point. And then now you can say the average kinetic energy of the particles or the molecules therefore doesn't change, and you can see that the temperature remains constant. That is the second mark. Okay guys, is that all? Yeah, that is all about the first 9 marks. Okay, let's try to speed up a bit. Now question 3 says an element X, okay, you can see there's a lot of element X, has 2 isotopes. Okay, isotopes, basically it means an element has 2 forms of atoms. Okay, and those 2 forms have the same atomic number, meaning the same number of protons, but they have a different mass number. Why? Because they have different number of neutrons in the nucleus. Great. Now the percentage abundance and atomic masses are given below. Okay, not a problem. Isotope 1 occupies 60.4% and has an atomic mass of 69.5. Okay, this one has a 39.6% and has a mass of 70.9249. Okay, now we're told you define an isotope. Okay, this is important. You will always come across this one. So 3.1.1, what are isotopes? Okay, isotopes are defined as atoms with the same atomic number but have different mass numbers. Okay, and this is because the mass number is determined by the number of protons, which is atomic number, and neutrons. So that means the difference between these is the number of neutrons contained. Okay, and then of course, if I was to tell you how to determine the number of neutrons, the number of neutrons is basically going to be the mass number, which we use U, minus the atomic number, isn't it? You just reverse that formula, or you make n the subject of the formula. So it's very easy. So remember, these are not usually given in the they're not given in the table, so you may have a few issues with them. So just know a few just know a few of the things that you need to know. So again, the key issue is here, same atomic number but different mass numbers. If you are to be asked why, they have different number of neutrons. All right, great. Now it says now calculate the relative atomic mass of element X. This is an important step or calculation for one to know. So please, when you learn it, whenever you learn it, make sure you know it. Okay, so I'm highlighting all of the important things, guys, so don't take them for granted. Okay, let's sort this one out. So how do we calculate? So we can say now the relative atomic mass is going to be equal to, remember, you're just going to take the percentage and multiply the number, and you add those two. So we can say this is 60.4. Now a percentage is over 100, isn't it? Okay, and then you're going to multiply this one by that mass number, 69.5252. okay? And then we're going to add this one. It's going to be 39.6. Again, a percentage is over 100. Then we multiply that by 70.9249. Okay, so that should give us our relative atomic mass in atomic mass units, but for your level you use grams per mole. So 60.4 divided by 100 into 69.5252 plus this one is 39.6 divided by 100 into 70.9249. So this is stuff you need to know, guys. So I'm getting 70, now remember we're told to 2 decimal places, so this is going to be 0.8, okay? So for you use grams per mole, okay? But sometimes you can use a U there, which is the atomic mass units, because we don't know exactly what is the measure there. But for your level, you use grams per mole. That is the smallest, or that is the SI unit for the mass number that we use. All right, so you're getting a mark for these two, and then you're getting the mark for the answer. And you are in a good position, okay? So you can see, guys, chemistry is easy only when you know what needs to be known, okay? Of course, it's very difficult to believe this thing until you see some experiments that explain this issue. Then it starts to, okay. So introduction of chemistry for grade 10s must be heavily experimental. Otherwise, you will lose the plot. You need to understand experiments, at least the basic experiments that you do at the school lab, so that you can understand that this thing, as much as it sounds non-real or unreal, it's actually not far from reality. Yes, we use models that try to reconcile some of the issues that come, but at the end of the day, it's not really far off, okay? Now, it says now identify our element. So write down the symbol for this element. So that means go to the periodic table and find it out. Now we use the atomic mass to find it. So let's go. We're going to use, now remember here, usually they round off to the nearest, so it's going to be 70. So we're looking at an atomic mass of 70. So these are unique to elements. You'll never find elements weighing the same, okay? So now let's see, this is 90s, 59, there is 70. So this guy here, Ga. Okay, so what is Ga? That is gallium. Is it gallium or gallium? Yeah, it's gallium. So you can see the atomic mass is 70. So you see, you look at this key. What is the bottom number? That's the mass number. So we calculated 70 to the nearest. So that should be the one, and it's always unique, okay? They will not share any of these things. So in the periodic table, there's no sharing, Papa. We only share groups and periods, that's all. But the identity is unique. So basically, this is gallium, so this is Ga. Okay, easy. So you will always be asked a question of identification of a particular substance. So again, make a habit of making sure you know what to use. You can use the atomic mass because it's unique to an atom or an element. You can use its atomic number, it's unique to an element. You can then use general information like the period and the group in which it belongs, as you saw above. Okay, guys, so you're getting your 1 mark there, and then we move on. 3.2 says the number of protons and the number of electrons, okay, and then the mass number, the mass number and the atomic number, okay, great, of aluminium. Now how is this aluminium? This is elementary, and then the next one is in ionic form, 3+ ion, okay. We know aluminium is an element of group 3, so it can shed 3 electrons. rather than accept 5 electrons that it needs to complete an octet rule. Okay, not a problem. So now it says, okay, as shown in the table below. Okay, some of the values in the table have been omitted. Write down the letters A to E on the answer book, and next to each letter the number omitted. Okay, great. So this one is aluminium in its ground state or natural state, and then we've got aluminium in an ionic state. So this means it has lost electrons, because to form a 3+, you know that aluminium must have lost electrons. So what happened here, we took aluminium, we added energy, right, ionization energy, to form a positive ion, which is a cation or cation. So we know that we ended up with Al3+, then plus 3 electrons. So that's the chemical formula responsible for the happenings here. I hope you understand, guys. So sometimes it's always nicer to, play around some of these things. Okay, now in its natural state, we can see the atomic number is 13, and then of course you can confirm that in the periodic table. It's definitely element number 13. So that means the number of protons is 13. But in its ground state, it's neutral. So it means also the electrons must be 13. So there are 13 here. Okay, so we can start answering and say, fine. A, this number of electrons in the ground state, it is exactly equal to the number of protons. Okay, so it's 13 electrons. Okay, now B, so we are told the mass number is 27, which is fine. Again, you will look in the periodic table, it is like that. Now the atomic number is what? Remember, the atomic number is defined by the number of protons in the element. So it has to be number 13. So this is just a number, so you can't say atoms, no. Okay, so C, now we're looking at the ionized form, but now we've formed a positive ion. So that means we stripped electrons away from the aluminium atom. So now what would be the number of protons? You know that the number of protons is the number of positive charges, so they have not changed because we only stripped electrons and not protons. So the number of protons remains the same, which is 13 protons. Okay, D. Now what do we know? The electrons. Now the problem is that we lost 3 electrons here, so it's going to be 13 minus 3, it becomes 10 electrons. Okay, great stuff. And then E, what is the story there? What is the atomic number? Again, the atomic number is the number of protons in an element or ion. So basically it doesn't change. Wait a minute. E is the mass number. No. So the mass number doesn't change, sorry, because it is defined by the number of protons and neutrons. And we did not tamper with those, as you saw above. So it will remain 27. So that's how you get those 5 marks. Easy 5 marks, guys. Just knowing your way around. Okay, so basically what this thing says, it says make sure you study what is an atom. Okay, there's a lot of theories as to what is an atom, plus electron structure, electronic structures of atoms. Okay, know that what is an atom, know the electronic structures, so study those, you will understand all of what I've just spoken about. Okay, now the SP notation, okay, this one is taken from the off-bow diagram, isn't it? Yes, of an unknown element. Once it is unknown, you know, most likely you'll be asked to identify it, is shown below. Okay, now the what you call the coefficients in this instance. Coefficients basically talk about energy levels. So once they repeat, that's the same energy level. You can see here, coefficients basically represent energy levels. So that is the first energy level. And then these two mean the second energy level. And then these two mean the third energy level. Okay, these are energy levels. Okay, I'm just trying to remind you in case you've forgotten. What we're talking about here is energy levels. But now the superscripts, what do they talk about? Well, the superscripts here, you don't call them exponents, you call them superscripts in this notation. These superscripts basically represent electrons. They represent electrons. And then of course the total is going to be all those electrons added. So it's 2 plus 2, 4, plus 6, 10, plus 2, 12, plus 6, 18. So remember, we talked of an element. So if it is an element, we assume a ground state. Okay, now what does that mean? The total number of an element in its ground state is equal to the number of protons. So I'm trying to push you a bit, guys. And then the number of protons represent the atomic number. So meaning in the periodic table, if you look for element number 18, it will be this element we're talking about. Okay, so it helps us to identify. So you can use the atomic number to actually identify what this is. Okay, and then now we know also that these two electrons in the outermost energy level, they form what we call valence electrons. Okay, the valence electrons are actually the electrons in the outermost energy level, and you can see here the outermost is the third. Okay, it's the highest energy level. And then how many are there here? 6 plus 2, they are 8. Okay, if there are 8 electrons, so we can already know that the number of valence electrons gives us the group. It means this element belongs to group 8 because there are 8 valence electrons. So if it belongs to group 8, we know that this is a noble gas, and then of course it satisfies the octet rule. In its outer energy level, it has 8 electrons, so all orbitals are fully filled. Okay, great information. And then now the outermost energy level here, we can see that it is the third energy level. Now this already tells us that this element is in period 3. A lot of information. So which means we can use the group number and the period number to identify it if we messed up with our number of electrons. So to make sure we don't go wrong, make sure you combine these three to identify when you can, of course. Now the question says here, for element X, write down the number of valence electrons. Oh, you can see that the valence electrons are the electrons in the outermost energy level. They are 8, so it's 6 plus 2, 8. So there's 8 valence electrons. So 3.3.1. So there is 8 valence electrons. Okay, great. So 3.3.2. It says the period where this element is found in the periodic table. So we look at where are these valence electrons. They are found in the outermost energy level, which is the third, guided by those coefficients. So that is the third period. Or you can say period 3, okay? 3.3.3. Now I told you the highest energy level in which the electrons occur. This is the third energy level as well. Okay, that is the third energy level. So can you see, this is nice, period and the highest energy level, you know, they mean one and the same thingy. Okay, misters and missuses, 3.3.4. now we're told identify it. We already know that we're looking for an element of group 8 in period 3, so we have to go to our periodic table. We can't just memorize it all, but yeah, I already know that that is argon, isn't it? Yes, but let's go and confirm it in case I'm feeding you lies. Okay, now we said we're looking for group 8 period 3, so the periods is the top 1 2 3 4 5 6, and then of course remember these ones, the lanthanides and stuff, they actually belong in period 5 and 6. Okay, but because of their different behaviors and that these ones are unstable, their nuclei can break apart, which is what we call radioactivity, so we use them to kind of produce our x-rays, but normally cobalt is what we use, but we can also use these ones for like some serious stuff. Okay, they can be even dangerous, so these ones actually belong there. So essentially, yeah, there's 7 periods, so this is period 7, but these ones belong in period 5 and 6, so don't make a mistake of confusing them. All right, so now we said group 8 period 3, and do you see it's AR? So AR is argon. Again, to prove that we're not wrong, it has an atomic number 18. All right, so that is argon, so that's AR. Okay, all right, okay. You know, so guys, knowledge is power. If you don't have knowledge, you don't have power. So we know that this is AR, which is argon. Can even, but they said symbol, so don't write argon, they said symbol. Okay, here's another question. 3.4 says write down the type of bond. Now when we say type of bond, we mean the intramolecular bond, not intermolecular force, that forms between chlorine and aluminium. So what is aluminium, guys? Aluminium is a metal. Okay, what is chlorine? Chlorine is a halogen, which is essentially a non-metal. Okay, so a bond between a metal and a non-metal is called an ionic bond. Okay, that is what you get. So you can either decide what type of a bond by looking at the particular elements involved. Okay, but I would like to educate you a bit on this one, but this is additional information. So let's say we want to draw the electronic structure of aluminium. Okay, and we want to just showcase this thing so that you can see how useful it is. Okay, so this is the 1s orbital, 2s orbital, 2p, which forms the second energy level. This is 3s, and then this is 3p, which forms the third energy level. Then there's also d orbitals, but we're not gonna go there for now. Now, how do we fill these ones? We know that aluminium is an element number 13, right, on the periodic table. Let's just confirm it. Okay, guys, I'm just gonna waste a bit of time now to try and expand a particular idea just for your benefit, nothing serious. So do you see the atomic number is 13? Okay, so that's why I know it's element number 13. Let's look at chlorine. It's element number 17 because its atomic number is 17. So we're going to be looking at these two to try and answer this question more fully. All right, so we know that if we fill these orbitals, it's going to be 1 2 3 4 5 6 7 8 9, 10. Pay attention to how I'm filling these. 11, 12, and then 13. Okay, so there is a rule in which you follow, so go and have a look at that. But you know, Pauli's principle says an orbital can occupy a maximum of 2 electrons, but for them not to repel each other, they must be in opposite spins, okay, because they create differing magnetic fields. Right. Anyway, let's not go into the details too much. So now let's look at that of chlorine. Chlorine is 1, 2, so don't pay too much attention here. I'm just working. So here we fill this one. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Because we know that chlorine is an element number 17. So the atomic number is 17. So do you see? Aluminium has 3 valence electrons in its outermost energy level, right? And can you see the deficit? It needs how many? 1, 2, 3, 4, 5. So it needs 5 electrons to complete an octet rule in its outermost energy level. So it's almost impossible to get that many electrons, isn't it? So it's much easier to shed these 3 electrons. So it can actually shed these 3 electrons easily than to add to these 3 to complete a stable. So for it to be stable, remember it is mostly stable when all energy levels are paired like this and fully filled. So it achieves that when it loses those electrons to just vacate those orbitals, then it becomes stable. So it's much more stable as a positive ion than as a natural element. Okay, this one you can see that it's only short of 1 electron, so it can't really shed 5 electrons. In fact, 5 plus 2, it can't shed all those 7 electrons to assume a stable state. It would rather add an electron in there to actually become more stable. So this is how we understand. So do you see now? There's going to be a complete transfer of electrons into this one, but then you'll have to multiply this by 3 because this can shed 3 to assume stability. This one can accept 1, so we'll need 3 of these to kind of, make this happen. But the type of bonding, because it involves electron transfer, it's an electron transfer, not sharing, then we call it an electrovalent bond. Okay, that's it for this particular section for now. And that's going to go. Now, I told you, draw the Aufbau diagram. I told you this is a German word for building up, not a person's name. Okay, for the chloride ion. But do you see now the chloride ion is negative. So what happened? To form the chloride ion, it means we add an electron to form an anion. Now we want to draw this thing. So it becomes easier now that we've already looked at it. So we will have 1s orbital, 2s. Don't worry that everything is flying. I'm just in trouble a bit. I'm in a bit of a troubled position. So I remember these must touch or kiss, whatever you want to say. But anyway, this one also has to touch. So we've got 1s, 2s, 2p, 3s, 3p. Okay, so we know that chlorine naturally is short of just 1 electron. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. But now we added an electron. So now, do you see the chloride ion is more stable than just, the chlorine atom in its ground state. That's why this gas exists as a diatomic gas instead of a single atom. Ne? Because for it to be stable, it has to be fully filled. Now you understand these things, ne? You understand. So of course, for each energy level, guys, 1, 2, 3, you're getting a mark for that. So this is chlorine. All right, and then if you were to write the SP notation just to add information, this is additional information. You would call 1s2 because there's 2 electrons there, 2s2 because there's 2 electrons, 2p6 because there's 6 electrons there, 3s2 because there's 2 electrons there, and then there's 3p6 because there's 6 electrons for the chloride ion. Not just chlorine, but the chloride ion. Okay, so if they were to say write the SP notation, this is what you would write. Okay guys, enough is enough. So it says now draw Lewis dot diagram to show the bond formation between aluminium and chlorine. So I'm glad I drew these ones, because if you did not, you'd be in trouble. Remember, the Lewis diagram uses valence electrons. So once you talk about Lewis dot, you use valence electrons only in your depiction. Okay, so that is what we need to be cognizant of. So let's just do something. Okay guys, let me just drink. Okay guys, I've had my drink, and in fact I also wanted to look at the race. So it's like 5 a.m. in the morning. There's World Superbikes racing in Indonesia. So as I'm doing your tutorial, I'm actually watching the race. So I just wanted to have a look. Seems like it's red flagged. Something happened. I wonder what happened. Anyway, I'm a bike junkie, so I ride a bike. I own a Honda 1000cc. So I'm a crazy freak. So be careful. So basically for Lewis dot diagrams, you're using only valence electrons, nothing else. So now we know that aluminium is an element of group 3, so it has 3 valence electrons. Spare that here they look, sort of like what you call, they look paired, but because there's empty spaces, they're not exactly paired, but it's just a rule that makes it look like that. So we know that if we represent open circles, those electrons, they are 3. Okay, those are the only 3 electrons of aluminium that can partake in a chemical bond. Then now when we bring in chlorine, chlorine has 7 valence electrons, as you can see here, the outermost energy level. So I forgot to label them: 1s, 2s, 2p, 3s, 3p, and you can see here the total is all of those 3s, 3p, they are 7. So it has 7 electrons, so we can use filled in dots. This 1, 2, 3, 4, 5, 6. Then the 7th one will actually form a bond. Of course, this one is mostly electronegative, so it will pull that bonded pair to itself than the aluminium. But here we're not really trying to be exact. And then if we bring in another chlorine here, because we need 3, it's going to be 1, 2, 3, 4, 5, 6, and then the 7th one forms that pair. And then we bring another one here, so it's going to be 1, 2, 3, 4, 5, 6. The 7th one is what bonds. So can you see the chlorine completes the octet rule, but for the aluminium it only has 6 valence electrons surrounding it. So it is happy like that, so we leave it alone. So this is what is important. So guys, know this thing, it is critical. Know how to do it. Okay, so this one doesn't really tell you whether you have a covalent bond or an ionic bond, but the only thing that will help you to know is that this is a metal, this is a non-metal, so these are ionic bonds. Again, you can check the electronegativity difference between the atoms there. It will tell you whether there's a complete transfer or there's sharing. Okay, so I think anything more than sorry, anything more than is it 1.5 or is it 1 is an ionic bond. But anyway, it doesn't matter, guys. Let's not be complicating matters anymore. You will learn those in grade maybe in grade 10. Yeah, I think in grade 10 you can learn them. So let's just see what is the electronegativity difference between these two, just for the sake of trying to be, you know, complete. The electronegativity is 1.5 and that of chlorine is 3. So can you see the difference is 1.5? So anything more than 1, I think, is a complete transfer of electrons. Or is it 1.5 or more? Something like that. So you can tell that this one is, so the electronegativity difference, E negativity difference, if it is more than 1, I think if it is more than 1, I'm not sure, guys, if I'm remembering correctly. Yeah, if it is more than 1 or 0.8 or so, this says this is an ionic bond. There's a complete transfer of electrons. But between 0.5 to say 0.8 or so, or 9, you know that this is a polar covalent bond. But guys, please double check these ones. I'm not too sure. I don't remember very well. Sometimes these things are distant, so I'm not gonna say too much for the sake of saving time. Okay, so how else could you have written this? You could easily say aluminium, okay, has these 3 because we need to use the valence electrons, and then plus chlorine. Chlorine has 7, 1, 2, 3, 4, 5, 6, and then has this unpaired one. Now you can see that this one can shed 3, this one needs 1, so we need to multiply this by 3. Okay, you can write it in a chemical formula, so to speak, and then we're going to have Al. Now it loses all these 3 electrons. It's going to be 3 plus with a chlorine inside here. But now this chlorine must be multiplied by 3, right, to balance, and then this one is going to have 1, 2, 3, 4, 5, 6. The 7th one will take the 1 from the aluminium, just to suggest that all those electrons are here multiplied by 3. So you can either show it as a chemical formula, so to speak, or you can show this one. This one is the commonest form that you will come across. This one is just you being artistic. Yeah, sometimes you've got to be creative. You can't be, you know, a simple person forever. So this is how you can score, guys, those 23 marks. So that is a bit of work, you can see. Okay, let's quickly try and do question 4. Now it says a section of a periodic table, okay, is shown below. So we know that this is group 1, this is group 2, that is group 3, that is group 4, that is 5, that is group 6, that is 7, that is 8. Okay, so you know those ones, and then you know that is period 1, period 2, period 3, period 4. That's the best you can do at this point. Then now we're told to write down the symbol as shown above of an element that is an alkaline earth metal. So do you see this question is coming back? We answered it in the MCQs, it's here. So alkaline earth metals are elements of group 2, but now this one must be in period 3. So you can see now this spells out magnesium, Mg. So to answer 4.1.1, we have Mg, mass times gravitational acceleration. Hallelujah, 4.1.2. All right, now show an element that will form an N-ion with A2 minus charge. So that means this one can accept a maximum of 2 electrons. Now, which elements can do that? Those are elements of group 6. these ones can take up 2 electrons. Again, you can draw the electronic structure of oxygen. You will see that it is short of 2 electrons, and if you add those, it acquires a 2 minus. So a bit of theory, unfortunately, will also be necessary. Now that is oxygen here, because in here we have oxygen only, but if there were 2, you would have a choice, 4.1.3. And then of course you were told to write a symbol. You can't write a name. Again, be careful of how the question is asked. Now we want an element that has the smallest atomic radius. Okay, now what did we say, guys? We said the radius increases down the group. The R here increases down the group, and it also decreases. R decreases across a period. Okay, so we can see that the highermost are the small ones, but now as you move from left to right, they become the smallest, isn't it? So now this makes helium the best guy for the situation. It has the smaller radius, but again, you know that there's only 1 electron in the 1s orbital and the 1 plus in the nucleus. Here there's more electrons and there's more protons. There's 2 and 2. So now the forces of attraction are going to be more, so that's what makes that radius smaller than a hydrogen. So basically this one is the smallest diameter or radius, but this one is the lightest in terms of weight, because it is, the molecular weight is 2, or the elemental weight or mass number is 2. This one is 1, but it is the smallest. So the smallest is helium, as you can see. Yes, hydrogen is small, but the smallest is going to be helium. So that is He. Sometimes it's called the alpha particle. Anyway, let's move on. This one has the highest electronegativity. Now the highest electronegativity, you can look in the periodic table, 4.1.4. You will see that it is fluorine. Okay, this is the most electronegative element in the periodic table, and the least electronegative is francium. Is it francium? Francium or frasium, something like that. Anyway, let's just go look, because sometimes you will not believe me. You'll be like, yo, now look at this frasium or francium. You see the electronegativity there? That is electronegativity, because that's the number on this side. The mass number is not determinable, it's difficult. So that is 0.7, and you can see 0.7 is the smallest electronegativity. But if you're looking at that of fluorine, it is, okay, maybe let's color it. So you can see that it is 4. There's no other electronegativity greater than 4. So it is the most electronegative. Okay, guys. So again, periodic table work, periodic table work, periodic table work. But now here, you're going to look and see that fluorine is also included there. Oh, right, okay. Now we want something that is a metalloid. So what is a metalloid? It means it has chemical properties of both non-metals and metals. Okay, so these ones are good to use as switches in our electric circuits. So they are very good to use as switches in the electric circuit. So again, you will know the utility of this. So which one is a metalloid? So what you do, you start from elements of group 3, right? From group 3, like boron, you think of boron. If you do something like that, you will know that it goes to, of course it does not continue. I think somewhere, which is it terullium, something like that, then you go down. So again, this one, you draw another parallel line here, it goes there, but once you get to that tellurium, which is around here somewhere, then you go down. Okay, so that usually gives us metalloids. Okay, so here the one that we have is essentially silicon, and you should also know this one theoretically. It's the easiest to remember. So 4.1.5, we know that it is silicon. All right, easy there. So let's keep moving. 4.2 says electron affinity, we talked about it, of chlorine is 349 kilojoules per mole. Now define the term electron affinity. So we already scratched a bit about this one. Electron affinity is defined as the energy, okay, let's just say minimum energy, this time released when an electron is added to an atom in ground or gaseous state. Okay, so that's it. So we can say electron affinity is basically the minimum energy released, not added, because we saw that it essentially is an exothermic reaction, so to speak, because it almost takes it spontaneously. So when that happens, it releases energy, right? So that is electron affinity. So again, it's something to ponder on and make sure you understand its significance. All right, great stuff. And then now we're told the electron affinity of element chlorine can be represented by the following incomplete equation. Chlorine gas plus dash going into chlorine something da 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 da. And by the way, to form, let's complete the statement. It's not complete. To form an anion or anion, okay, or we can say negative ion. Great, so that one is possible. Now basically we are given this one, we say they are telling us now copy this and fill in the missing spaces, so that's fine. 4.2.2, we're going to have chlorine gas here plus, now remember we said we are adding an electron to form an anion, so it's going to be chlorine minus, of course it can still be a gas, it's not a problem, and then plus we're releasing, we're told here that the electron affinity is this one, so it's 349, so we're going to write the 349 kilojoules per mole. So don't write the 400, it's not correct, okay? They're just writing it to mess with your head a bit. Okay, so that is what was missing, adding of an electron and showing up with an anion. Okay, 4.3 says atoms of francium, yes, that is francium, have the lowest energy required to remove an electron from its atom to form positive ions. And we already defined that one, that's ionization energy. Write down one word or term for the underlined phrase. We said that is ionization energy. Okay, great. So we already defined it somewhere, so it's coming back again. So like I said, if you ignore MCQs, guys, you will feel like you are burning. I promise you. You start to feel like you are burning. This race is becoming nice, guys. Yes, I want to pause for a second, guys, and watch these last 4 labs. Just a moment. Okay, guys, let's continue. So the race was hot, so I couldn't resist looking at the final stages and also to listen to the post-race interviews, okay? It was a nice one. My favorite rider, Toprak Razgatlioglu, won the race. So let's hope in race 2 he does wonders as well. Okay, now let's have a look at this question 4.4. Now we're told to write down the formula, okay? Write down the formula of the compound formed when lithium combines with oxygen. Lithium is an alkali metal. It reacts with a non-metal, which is oxygen. So we'll be forming some kind of a ionic bond, isn't it? It's an ionic bond, actually. It's not some kind. Okay, so now what do we need here? We need to, I'm going to take shortcuts, guys, but please revise electronic structures of these elements so that you can understand why it is so. So now lithium is an element of group 1. Elements of group 1 can shed 1 electron to form a lithium 1 plus, okay? Oxygen is an element of group 6. It accepts 2 electrons to form a 2 minus ion. Now we need to balance the charges. So the lithium here is going to have to be multiplied by 2. So the 2 is shown as a subscript, oxygen there. So lithium oxide is like that. So because this one is 1 plus and this one is 2 minus. So to balance these charges, you have to multiply the lithium with a 2. Of course, don't show these charges, but this is the understanding that you have. Again, you need to understand the group, because the group state will tell you how much electrons can it lose. Then this one can lose 1 at a go, so it forms a 1 plus ion. This one can accept 2 at a go, and it forms a 2 minus ion. Then you just try to balance that by manipulating which one must you increase and which one must you leave alone, or whatever. Both. Sometimes you may have to do something about the both of them, but at this stage it's easy. Lithium oxide is Li2O, okay? That is it. 4.4.2. It says now when calcium combines with fluorine, calcium is an element of group 2, so it can shed 2 electrons, right? Right, and then it forms a 2 plus ion. But now fluorine is an element of group 7, so it can only accept 1 electron to assume stability. So what happens to fluorine? Therefore, we have to multiply it by 2, because calcium will give us 2 plus. This one would be a 1 minus. So now to balance the charges, you have to multiply this one by 2. But like I said, you don't show the charges. Don't show the charges. That is not correct to do. So we have calcium difluoride. You can say calcium fluoride. Here you can say dilithium oxide, but this is just lithium oxide, okay? Let's keep it simple. Lithium oxide and calcium fluoride. But these are there to just balance out the charges, as you would see how electrons are going to shift around, okay? So guys, this is also important to know how to write chemical formulas or molecular formulas of substances, and exactly how do they form. All right, great. I hope you guys understand. Anyway, now let us continue. So guys, we're almost behind time, but I'll try to speed up. Now question 5 says consider the following reaction. So we've got a copper solid, oxygen gas, and then we've got a copper oxide here on this side. All right, but now let's see if it is balanced. Basically there's 4 coppers, 2 by 2 is 4, there's 2 oxygens, and then there's 2 oxygens, so everything is balanced. So this is a balanced chemical equation. So the question says write down the chemical name of copper oxide. So this means we have to show now what is going on. Remember, oxygen, it's an element of group 6, so it can form the 2- ion, but now there's 2 of them, so it's going to be 4-, right? Copper here at this point, you can see that it's doubled, so it means it's a copper 1+, okay? It is the copper 1+. So to increase this one, you get a copper 2+ to balance this one, and then of course we're making 4 of them to balance the 4- of the oxygen. Like I said, this is 2-, 2 times 2 is 4-, and then this is 1-, and then 2 times 2 is 4, so that's going to be 4-. But don't show these things. So it means this is the copper that makes 1+. Again, please guys, make a habit of remembering a bit of theory, because when you study metals, you will know that copper occurs in 2 forms. The copper 2+ and the copper 1+. Okay? So those are the 2 isotopes of copper that you're going to come across. And then in terms of what we call Stoch notation, you write it like that when you mean the one that makes 2+ ions. Okay, let's just write it here. So the copper that makes 2+ ions basically is written like copper 2. We use what we call the Stoch notation. Okay, and then the copper that forms a 1+ ion, we call it a copper 1. Okay, using the same notation. Okay, so basically this is the one. So you will learn about this theoretically, because sometimes it's very difficult to tell, but if you inspect what is going on here by of course knowing a few oxidation numbers, which essentially you know where it comes from. Okay, so basically this is copper 1 oxide. That's what they're looking for here. So 5.1, we've got copper. Of course they said chemical name, so this is copper 1 oxide. Okay, what is key is knowing that is copper 1 instead. Okay, great. Now let's move on. That is the name that they were looking for. Now it says classify the above reaction as a synthesis or decomposition. Remember, when you're taking 2 reagents to form one product, that is synthesis. Okay, otherwise decomposition is the reverse of this one, taking this one and breaking it apart. So basically 5.2 is a synthesis. Okay, that is it. 5.3, what is the story now? Using a calculation, prove that the law of conservation of mass is valid for the above reaction. Again, if you think about this law of conservation of mass, this is something that came from the models, the atomic models by John Dalton. So please read about the atomic model by John Dalton and how he actually found out that in a chemical reaction the mass was conserved, although he could not explain in his model how the atoms combine in the ratios that they do. So please read such things as well, they are very important. Okay, let's look at that equation for Cu solid. So we've got for Cu solid plus oxygen gas, we formed 2 Cu2O. Okay, great. So what is that? It's a solid. Yeah, it's a metal oxide. It's a solid. Anyway, so now what do we do here? We can say this implies what? We know that this is going to be 4 into, what is the mass number for copper? Unfortunately, you need the periodic table. Sometimes it's hard to remember this. Copper is 60 63.5. Okay, so others you will know by heart, but others you will need reminding. So this is 63.5. So basically the coefficient here is quite critical at this point. Normally when you calculate the mass number, you don't include it, but because this is a critical step now of trying to identify what's going on, it is important. Okay, plus now the mass number of oxygen is going to be 16 times 2 because it's a diatomic gas. So this is equal to, again, 2 into, okay, actually I'm making a mistake, guys. I think I am making a huge mistake. When you're calculating the mass number, you don't use coefficients. Yeah, man. You don't use coefficients. Sorry, guys. I'm forgetting things. So you will see that as you go along, you don't use, but subscripts, yes, they are important. Then here you're going to have copper, which is 63.5 times 2 here, plus oxygen. Now oxygen here is 16. Okay, so please, coefficients, forget about them, even though they are there, but when you're doing the mass number calculations, do not include them. Therefore, let's see now. Let's put it into the calculator and see. So we've got 63.5 plus 32. That gives me 95.5 is equal to, then let's do this one, 63.5 times 2 is 127 plus 16. I think I'm getting myself into trouble. It's 143. So yeah, no, we can't. Okay, guys, unfortunately, remember, we're not doing the molar ratios. Okay, maybe let's do the right thing here. So unfortunately, yeah, it doesn't balance out, so these ones have to come in. Okay, I was making a mistake. Sometimes these things are a bit too distant. So when you want to prove the mass conservation, you use everything there is. But when you're calculating molar ratios, you don't include these coefficients. Okay, so this is 4 into 63.5. All right, plus 32 for oxygen. This gives us 286 on this side. And then here we're going to have 2 into 63.5 times 2, okay, plus 16. And then I'm getting 286 as well. Yeah, now it makes a bit of sense. Okay, I almost made a meal. So we can say, therefore, the law of mass conservation in a chemical reaction holds. Okay, of course, or you can say it's valid because the mass before should be equal to the mass after. I kind of made a bit of a silly error because I'm so used to calculating molar ratios and stuff, and then it becomes a bit of a naughty situation. Okay, so forget about that bit of a mistake. So again, guys, this is an NB. Please read about the atomic model as described by John Dalton. There's also an atomic models by Niels Bohr. Is it Bohr? Bohr. It's Niels Bohr. Okay, this guy was a Swedish, was it a Swedish Danish? I think it was Danish, from Denmark. This one is a Danish chemist or something. His ones was that one of talking about the radius and orbitals orbiting around the nucleus. And then Dalton said a lot of other things that, yeah, were sometimes difficult, but it mainly explained the theory of the conservation of mass, although he could not explain, or his model could not explain, the molar ratios of those atoms in a compound. Okay, read Niels Bohr, and then of course I'm just giving you key areas now, and then also read something about Ernst Rutherford. Okay, and read about his master or teacher J.J. Thomson. Okay, read about all the experiments they conducted, but these two did a lot of work that we still see, especially this Australian. This guy was Australian actually, but they say he's American. You know, Americans are stealing people. This guy is Australian originally, but he went to England to be taught by J.J. Thomson. These are the guys that experiment. These are the guys actually describe that there is actually a negatively charged particle. And then of course there's another guy who used cathode ray tubes to prove that. Okay, I forgot his name now, but there's plenty of these names, but anyway, you'll come across them as you learn. Okay, let's move, guys, before I waste too much time. So please read something about J.J. Thomson. You're not Thomson, it's Thompson. Okay, and then Ernst Rutherford, Niels Bohr or Bohr, whatever that is. I don't know, Bohr, it's actually wrong like this. Niels Bohr is like this, yeah. I think it's like that. I don't remember, guys, but you read something about these dudes. Then you will become a genius. Okay, 5.4. Now we're told here 20 grams, okay, of copper completely react. So once it completely reacts, it's a rate limiting reagent, okay, with a 250 centimeter cubed of hydrochloric acid. Okay, fine, of unknown concentration, so they may want it according to the following balanced equation. So luckily it is balanced, but you can double check how many coppers have got. 1, and then how many hydrogens have got. 2, and then there's 2. How many chlorines have got? 2, there's 2. So usually when you're reacting a metal and an acid, this is usually the target to produce hydrogen gas. Okay, you need to learn about those things. And a salt. Okay, this is not a this is not what was the word now? It's not an acid-base reaction, but it's actually a redox reaction. It's an oxidation reduction, because if you're looking at copper, its oxidation number is 0, but here it is mixed with 2 chlorines. Chlorine carries a 1- times 2, it's a 2-. So this means it's the copper that gives 2 electrons to form a 2+ ion. So can you see here the oxidation number of copper is increasing, while that of hydrogen, if you're looking at hydrogen, it is 2+, because hydrogen is a plus, times 2, it's a 2+. Okay, now hydrogen here on this side is 0, so it is being decreased. So when the oxidation number decreases, we call that one reduction. What about chlorine? Chlorine is 2-, and then it's 2-, so basically it is a spectator ion. Nothing has changed. Okay, these are some of the things you want to think about as you work your magic here. So you know that there's oxidation and reduction taking place at the same time. And most of the time, ionic reactions are redox reactions. But anyway, let's leave it at that. Define the term concentration. Okay. Now you may forget what a concentration is. If you remember the chemical formula from the formula sheet, you basically are taking number of moles per unit volume. Okay. And you just describe that. You will be sorted. So 5.4.1. So now if we're trying to define the word concentration, okay, It is an amount of solute of a substance dissolved per unit volume of solvent. Okay, so it's a solute against solvent. Of course, this is what forms an aqueous solution. All right, great stuff. So we are dissolving. So I say unit volume because remember here you can use liter, you can use decimeters, you can use centimeters cubed, so it can be anything, but normally we use a liter instead of just any volume. You can cite an amount of a solute of a substance dissolved per liter of a solvent. This is the standard stuff, but sometimes you may forget this one. You are safe when you use unit volume because you know that in grade 10, 11 and 12, when you're using molar concentrations, you actually use decimeter cubed instead of liters. Okay, if you're given in liters, you have to convert to decimeter cubed. Great stuff. Again, guys, easy 2 marks textbook work here. 5.4.2. What is the story now? Calculate. Okay, this is a stoichiometric stuff. Again, this is stuff that you need to make sure that when you come across it, you learn it well because it will take you through to metric. And in fact, the greatest marks in chemistry that you will get in metric and grade 11, they come from stoichiometric calculations. So please learn these things and understand them well. All right, so we want the concentration of hydrochloric acid. So we need to look at the molar concentrations, the molar ratios of copper versus HCl, because we know something about copper. So we can see here, if it's not written, there's a 1 there. So 1 mole of copper reacts with 2 moles of hydrochloric acid. So we can say from the equation, we can see that 1 mole of copper reacts with 2 moles of HCl. Okay, these ones you know by looking at the coefficients, not subscripts. Okay, please. And then what does this mean? This implies, because remember we want the concentration of HCl. So now we're going to use some theoretical techniques. So it means that the number of moles of HCl is going to be equal to, remember now this one is going to be 2 times the number of moles of copper. Okay, that is the implication here. And then this is 2 into number of moles is basically number of moles, is mass over molar mass. Okay, let's just go on here. This is 2 into the mass. We're given that it's 20 grams, right? 20 grams, so mass in grams. Copper, we know that from the periodic table, the molar mass is 63.5. Okay, so let's get the number of moles. Guys, I'm losing time. I'm too relaxed and it's dangerous, so I should not be doing like this, but I'm taking the chance to teach you something in this introductory lecture. So basically this one is safer to leave as 8/127 mole because you don't want to round off too soon. Okay, and then now let's create a bit of working space by separating these two. So we can say this implies that the concentration now of HCl is going to be equal to the number of moles of HCl over the volume. But now this volume, we know that we're going to have to convert to decimeter cubed. So what is the number of moles here? It's 80/127. Okay, Now this, we can use it like that, divide by. Now the volume is going to be 250 divided by 1000. So you change it to decimeter cubed by dividing by 1000. So now let's do this one. So we're going to say that divide by basically 250 over 1000. Okay, at some point I will show you how to do these conversions confidently. I'm getting 2,52 mole per decimeter cubed. Okay, so that is the molar concentrations for your syllabus. You do them per decimeter cubed. So you can see here it's a two-step type of a question and it's a bit hectic. So again, noticing this is important, but what is even more important is the implication. But normally you get a formula, a mark for the formula, and then the intermediate answer, which is the number of moles right there. So I forgot the substitution is important. So we've got 3 marks there. And then here you're going to get a mark for we've got how many marks? 1, 2, 3, 4. So we need 2 more. I mean, we used a different formula, so probably 5 and then 6. You can't really get a mark for substitutions because even if you're using different formulas, it's usually not that significant. But again, they will decide where are the most marks. But for me, I wouldn't really give a mark for the formula, right? But what matters for me is this 2 in front of the number of moles. So you would get here 1, 2, 3. So 1, 2, 3, 4, 5, and then 6. That is personally how I would mark it. But again, you will have to look for the memorandum, guys, to see the marking guidelines that are official so that you do not get misled by this guy. Some of the things for me are arbitrary, but most of the things are actually, what is key and is core to the subject. All right, let's look at question 6. During a demonstration, to show the difference between physical and chemical change. Now, physical change, you can see that you can move from one phase to another. You can increase the kinetic energy or decrease the kinetic energy, meaning separating the molecules and all that, but you're not really breaking any bonds. But chemical change, the bonds need to break, meaning the intramolecular forces need to break, and then new ones have to form. That's when we talk of a chemical change, meaning we're talking about an ionic bond, a covalent bond, or a metallic bond. Okay, now experiment 1. Okay, ion filings are heated, so energy is added here with sulfur. Okay, so now once we heat 2 together, that means chances are we are more likely to break the intramolecular bonds and we are likely to form new ones. So here a chemical change is likely. I'll say likely, it's not a sure case. It will depend on also whether this energy is enough to achieve that. Okay, experiment 2. What is going on here? Experiment 2, we've got ion filings. They are just mixed with sulfur powder. So actually what we are resulting into is a mixture. Okay, a mixture, there's no chemical change, but there can be a physical change because depending on the polarity of these substances, there may be some intermolecular forces of attraction, but there are no chemical bonds forming. Okay, so basically this is a mixture, so that means there is no bonding. Okay, no chemical bonding taking place, but intermolecular interactions can occur. Okay, great. Now we're asked here, which one of the above experiments is an example of a chemical change? Of course, it's likely to be, I don't like the part that says it's an example. It is most likely an example, because we don't know how much heat was given. Was it enough to result into a chemical change? But between the two, I would choose one. Okay, so we can say here 6.1, it is experiment. It is experiment 1. So that is most likely. I think that is the safe word you can use. Give a reason for your answer. You can say here it is likely to have breaking of chemical bonds and formation of new ones. Okay, the hint here is that we added energy. Which is in the form of heat energy. Okay, so you know that the collision model of chemical change. So we're using the so-called the collision theory, or they call it the kinetic model. Essentially, once we use heat energy, we are going to cause molecules to start moving, and therefore they will have regular collisions. And then once there's regular collisions, there are more chances for effective collisions. Effective collisions are essentially these chemical bondings we're talking about forming. Okay, not a problem. So you understand what is going on, guys. So there are some key parts that can give you a guide. You make sure you understand and know them. Now it says write a balanced equation for the change in experiment 2. Okay, so basically ion filings, ion is Fe naturally, plus we're going to just add sulfur there, and then all we end up with is ion sulfide. Okay, but we're not going to express anything here because we don't care whether they are mixing in any particular ratios. But remember, this is just a mixture, so we just show it like that and we leave it alone. Please don't do anything. Remember, ion also can occur in different forms. It can form 2+ ions, it can form 3+ ions, it can form, is it 1+ ions? I'm not sure about that one, but yeah. So here you're not gonna do molar ratios to suggest that there's bonding taking place. Okay, once you include molar ratios, you're suggesting that there's bond formation. If you don't include them, it means this is just a mixture and you don't care about the rest. All right, that is the most important. The key here is to not to include molar ratios. Okay, if you don't include molar ratios, you're suggesting a mixture, so to speak. This is of course something you want to think about, but be cautioned. I may be wrong. Ask your teachers about such things so that you don't run into a problem and you don't know what to do now. So I would say again here, go and ask somebody who knows better than I do, which is an educator, or consult study guidelines, exam guidelines, or your textbook. Okay, I'm a human being. I am allowed to fault a bit, but I do my best to limit that, and you will also see it yourself when I'm making a mistake. Anyway, name a method to reverse the change in experiment 2. Okay, so remember now, when you have a mixture, there's something called fractional distillation. I'm not sure if my distillation is correct, but let's write it properly so that you know what this is. This is I'm not sure if it is double L or it's just a single L. Yeah, sometimes it's a mess. But fractional distillation, actually you use heat in the knowledge that certain substances in this mixture will evaporate, okay? So basically, you know that certain substances will evaporate at a certain temperature, while other ones have a higher boiling point or higher melting point, so they may remain behind. But this is what you do in the industry. Okay, to some extent in the lab. In the school lab, you can still do some, but not all. So yeah, you can think of this technique. This is usually how you separate these things. But if you think about it, what do we know about iron? It is ferromagnetic, meaning it becomes drawn to a magnet. So if it is ferromagnetic, this means we can use a magnet. So for 6.4, I mean, this is the simplest so far. So we can use a magnet to attract the ion filings, okay, since they are ferromagnetic. Okay, so guys, there are some terms that when you read, sometimes they are not exactly explained. So the key thing is, when you study, have a dictionary. Okay, have a dictionary, Baba, so that you make sure you understand what is being given. Once you see a word you don't get, please use your dictionary. There's even now internet, your phones are quick. You can just go into Google. If your dictionary is not where you are, then you can just double check what is meant by ferromagnetism or ferromagnetic state of certain substances. Then you can easily follow and understand a description of an experiment or a description of a certain concept that contains words that probably are easy to misconceive. Alright guys, this is how you get those 6 marks in this question. Let's go to question 7 quickly. Question 7 says formation of sulfur trioxide. Then now this one is a step in the so-called contact process. This process is basically for production of sulfuric acid. Okay, in the industry, not in the lab. Okay. In the lab you can do it though. We've done it in the lab. Okay, but in the industry we call it the contact process. But in the lab you don't call it the contact process, because we don't even use the contact catalyst. So basically the reason for that word contact is because we're using vanadium pentoxide. So it's divanadium O5. Okay, this is a contact catalyst. It's called a contact catalyst. Again, like I said, use your dictionary to understand what is a catalyst. It is a substance that facilitates the speed of a reaction without itself taking part in the reaction, isn't it? That's the definition of a catalyst. So because of the vanadium pentoxide, then this process is called a contact process. Now, yes, but again, this was part of the so-called inorganic chemistry, so I don't know if you guys are doing it, but either way, I'm just giving you a heads up of where you're going. Sometimes when you're doing chemical equilibria in grade 12, this appears more often than not. Okay, now this is represented by the balanced equation. Again, you've got two sulfurs, we've got two oxygens times 2, that is 4, plus 2, that is 6, and then here we've got 3 times 2, that is 6. So it's definitely perfectly balanced. Okay, we can accept it. Now I told you identify the element in the above equation. Element basically means naturally occurring form. Okay, sulfur trioxide and sulfur dioxide gas are produced gases. They don't naturally occur, right? But oxygen does naturally occur as a diatomic gas, so we can easily call it an element. So 7,1, we can say oxygen. We can just say oxygen. In fact, they said element, so be careful of certain things. You can just say oxygen to avoid a formula. Just say oxygen, because if you write O2, they said element, oxygen. The others are sort of like compounds, so it's a bit of a situation. But anyway, you can even write O2, it's fine. Draw Lewis dot diagram of the oxygen molecule. Okay, see, this one is coming back again. So if you fluffed it, you are fluffing it again. So there is one oxygen, there is another oxygen. Okay, now oxygens are elements of group 6, so they have 6 valence electrons in their outer energy structure. So we've got 1, 2, 3, 4. Okay, let's try to make sure that these are open circles. 1, 2, 3, 4, 5, 6, and then this one is going to have 1, 2, 3, 4, 5, 6, and then of course the bonding is going to happen with these two, so that each one is surrounded by 8, because now it's going to be 2, 4, 6, 8. This one is going to be 2, 4, 6, 8. So they actually acquire the octet rule, but now there's going to be a double bond. There's going to be a double bond, but don't show the double bond. They said Lewis structure. Okay, so that is it. Maybe 2 marks for those bonding pairs. Not a problem. So we're told here 7.3. During the above reaction, okay, 10 grams of oxygen react completely. That becomes the rate limiting reagent with sulfur dioxide. Okay, so meaning if the oxygen runs out, the reaction stops. Okay, calculate the number of moles of oxygen that reacted. Okay, so the number of moles of oxygen that reacted is going to be the mass of oxygen over the molar mass of oxygen. Now, the mass of oxygen was 10 grams, right? Over, and then, okay, yeah, I'm worried about space here. So the mass of oxygen, the diatomic gas, is going to be 16 times 2, which is going to be 10 divided by 32. And then what is that? Let's see. 10 divided by 32 is basically, again, we were told to round off your final numerical answers to at least 2. So this is 0.31 mole. So that is the answer for the question. That is the answer for the question. So that was easy, standard 3 marks, formula, substitution, answer. But of the substitution, what is most important is the molar mass, isn't it? Yes. 7.3 0.3.2. What is the next question? The theoretical yield of sulfur trioxide gas. Okay, the sulfur trioxide gas, when you say theoretical, we're going to use the molar ratios basically. Now, what do we know here? Of the reagents, we know oxygen, and then we also know now that the number of moles of oxygen, the coefficient is 1. 1 is to 2. 1 mole of oxygen produces 2 moles of sulfur trioxide gas. We start by saying that 1 mole of oxygen produces 2 moles of SO3. Let's just not write too much English. Sulfur trioxide gas. Okay, so basically, what does this imply? We're more interested in sulfur trioxide. It means now the number of moles of sulfur trioxide gas is going to be 2 times the number of moles of oxygen, right? Which is going to be 2 into 0.31. This gives us 0.62, right? Mole. Great. So now that we have the number of moles of sulfur trioxide gas, now we want the percentage yield. We can say therefore the percentage, the theoretical yield. Therefore the theoretical yield. Remember, we use mass in reality because number of moles, really doesn't make sense. It's going to be equal to, remember, this is going to be the mass. It's going to be the number of moles multiplied by the molar mass. This is going to be 0.62 multiplied by. Now, sulfur trioxide gas is the molar mass. Sulfur is, I think it's 32. Plus oxygen times 3, so this is 16 times 3, okay, which we're running out of space here. Again, consult the periodic table, guys, to double check things, but I trust my memory of this one. So this is going to be 0.62 into 32 plus 16 times 3. So we're getting here 49.60 grams. So normally this is what makes sense in terms of production, isn't it? We measure the mass in grams. But you could still leave it at number of moles, but then it becomes a bit tricky because now when you talk of theoretical yield, please remember you want the mass in grams. So that's why I'm converting. Again, how many marks are we getting here? 4 marks. Great stuff. So I think determining the number of moles is important. Getting the formula, substituting, and finding the answer is what is important. The rest is what you need to be able to understand. Okay, 7.3.3. Okay, guys, we're almost at the end. So it says calculate the percentage yield. You see, once you see that, it's coming to that. Now, if 40 grams, remember, theoretically, we produced 49.60, but actually, we got only 40 grams. So do you see, it's not so far away. It's just a margin of the answer. So it can be more, it can be less. It doesn't matter, depending on the conditions. All right. So now we want the percentage yield of sulfur trioxide that is produced at the end of the reaction. So we know that, of course, the percentage yield is going to be the actual what is that? The actual yield over the theoretical multiplied by 100%. So these are some of the things you need to make sure you know, guys. The actual yield, we are told now it's 40 over 49,60 times 100%, which is going to give us the percentage yield. So this is 40 divided by 49,60 times 100. So that gives us 80, to 2 decimal places 65%. So do you see, it's still a very great percentage. I mean, 80%, come on guys, it's what you would call a distinction, isn't it? If you scored 80%, that's a distinction, so it's good. So it means really we produced quite good. So our calculations are not really bad. I mean, if they're 80% correct, I mean what is that? Is good stuff. So again, here formula, substitution, answer, usually standard 3 marks, and that's how you get those 13 marks. Okay guys, let's end this thing, it's been long. Now, an inorganic compound, okay, has the following percentage composition. Okay, 43.39% of sodium, 11.32% of carbon, and then 5.28% of oxygen. Now it says determine the empirical formula. So again, define the empirical formula. We've already bumped into it. 8.1. The empirical formula, okay, is basically defined as the simplest whole number ratio of atoms in a molecule. Okay, not molecule. Yowen balanton. Molecule, okay, or compound. I normally don't like that word, but yeah, whatever. So this is the simplest whole number ratio of atoms in a molecule. So that is essentially an empirical formula. So do you see it's coming back? We defined it and used it or applied it. Now they want it back. So do you see the marks are just circulating over the same concepts? Now determine this empirical formula. So again guys, this is a question that you must can note because if you don't note this one, it's one of the things that are going to cause you problems in matric, because sometimes this is something you're going to have to deal with. Okay, the last question kind of used this idea. Okay, now how do you determine that? So first of all, when you given percentage compositions, so all you do, you just assume 100 grams of pure substance. Okay, you assume that you were given 100 grams of pure substance. To then talk of percentages, now of this 100%, because 100 grams will give us 100%, right? Now when you're looking at sodium, it's only occupying 43.39%. So essentially, if we want the number of moles of sodium, we're going to use mass. Now what is the mass? Remember that composition, it's over 100. So this basically tells us that the number of grams there is just going to be 43.39. Then we divide by the molar mass of sodium. The molar mass of sodium is what? 23. Ne? Think so. Let's just double check. It's not very far. Yes, it's 23 grams per mole. So it's the mass number. So this mass, how did you get it? You just said this thing here over 100, right? Right. And then it gives us basically, what am I saying now? I'm not remembering myself, but yeah, whatever guys, hey, something is happening here. Yeah, doch. Basically going to say this thing over 100 times 100 because we're assuming 100 grams of the mass. So we just take the percentage and multiply by that. It gives us the mass. So this over 100 times 100, the hundreds cancel out to remain with that. So please know how to work with ratios and proportions. So great. So now 43,39 divided by 23 is giving something like 1,8 to 2 decimal places. It's going to be 1,89. Okay, not a problem. What about the number of moles of carbon? So again, we're going to do the same here. We just take the percentage of carbon, divide by 100 and multiply by 100 grams of a pure substance. The hundreds cancel out, so we only remain with that 11,32. So this is going to be 11,32 grams divided by the molar mass of carbon is 12. Okay, it's from the periodic table. So let's see, 11,32 divided by 12. I'm getting 0,94. Remember, this is mole, okay, because this is grams, this is gram per mole, so you can see why it is moles. Now let's look at the number of moles of oxygen. We are told here it's 45,28, so it's going to be basically 45,28 over the molar mass of oxygen is 16 grams per mole. So we've got 45,28 divided by 16. So I'm getting here 2,83 mole. Okay, great stuff. So once we've got it in moles, remember the molecular formula and empirical formula, we're talking about molar ratios, right? Now, which one is the smallest here? This one is the smallest. So we divide throughout by the smallest. Okay, and then we divide by the smallest here, 0,94 mole. The mole cancels, so that we can get our molar ratios. So we can say, therefore, the molar ratios here are going to be approximately what? Now let's see. So here you can just say molar ratio here. Okay, this implies that the molar ratio is, we just divide. So I'm just complexing steps, guys. I'm being silly, I know. You'll have to forgive me for this one. I always love a systematic approach, but I'm tired right now. So let's see, 1,89 divided by 0,94. So this one, you're going to take the nearest whole number. So this is approximately 2. Okay, because it's 2,01. So you always take the nearest because it has to be a whole number. Please. And let's do this one, 0,94 divided by 0,94 is 1, isn't it? Then let's look at this one, 2,83 divided by 0,94. This one gives us approximately, don't do things that I didn't send. I'm getting 3,01, so it's approximately 3. So now once we have those molar ratios, we can safely say, therefore, the empirical. Oh, therefore, the empirical formula is such that we started with sodium, so it's Na. Now the ratio there is 2. Carbon is 1, we don't write it. Oxygen is 3. So this is Na2CO3. This is like sodium carbonate, but remember, this is not the actual, it's the simplest. So for us to get the actual, we need to know the mass of the actual substance, the pure substance. Here we made an assumption of 100 grams, but we need an actual mass. because once we have an actual mass, then we can divide this, we call it estimated mass, by the actual mass to get a ratio there. Again, we want a whole number, then we multiply into this to get the correct molecular formula. But the empirical formula is correct like this. So how many marks are we getting here? 5 marks. So what is important, guys, is getting to these guys here, and then to get this one right. And then where are the other gymnastics that are important? So we've got 4 marks there, but I think this first step here, we can just give a mark for it all by knowing what to do. So guys, this is NB. Please know how to do it when you finally cross paths with it. Otherwise, this is the end of my attempt to introduce chemistry to you grade 10s. And by the way, welcome to my channel. And if you like what you see, please do subscribe into the channel to make sure you don't miss out on what can help you throughout your high school chemistry. Of course, I will do some physical science papers as well. Then I'll do maths papers as well, so that I build you up from already grade 10 through grade 11 to grade 12. At least you can spend 3 full years with the channel, right? Because matriculants, they are visitors. They just spend 1 year and they're gone, right? So to create a bit of stability in the channel, I think it's fair to start from a bit lower, then grow you guys into matric. There's already materials though for matriculants, so if you have a sibling or a friend or a neighbor who's doing matric, tell them that there is this channel here where there's a lot of detailed reviews of past exam question papers in an attempt to integrate information. I really do not have the luxury of time to do lessons so that I can build you from the ground before we get to these questions. So I'll always assume you know a little bit, but I'll try to highlight the most important areas and also to review and revise with you some of the key areas that are a bit technical for most. Otherwise, guys, I hope you enjoyed the video. You're gonna give it a thumbs up. Please subscribe into the channel if you feel this is a cup of tea you can drink all the more and repeat it as often as you want. Otherwise, do the right thing. Study, study, study well. Okay, don't spot information, don't skim and scan. Study, meaning study well, meaning you want to understand. Okay, first understand. Okay, and then once you understand, you commit to memory. Don't commit to memory without understanding. That's a disaster. Okay, and then once you commit to memory, don't want to only commit to memory, then you revise. Okay, once you revise, you're using notes. Okay, or you can even reread. Sometimes you may read the first time and think you understand, but when you read the second time, even areas that maybe were seemingly a bit complicated, it's because you didn't read with a lot of concentration. You were getting distracted along the way because, you know, a new idea, sometimes you hang on to what seems easy to understand, what seems a bit technical. You kind of feel like, okay, this one is spoiling the party. You jump it. So when you reread or revise notes, sorry, that is a way of revising, right? And then once you've done that, you exercise. Exercise. How do you write exercise? Okay, This is when you use sample questions in your textbook and past exam question papers. Okay, so yes, I've finished my 3 hours, which I hoped honestly to get to, because the purpose was to lay the foundation. But as we do many others, I will not sit as strictly as I have on this initial one. So as I said, when you study well, guys, this is what you do. You study to understand the first time around. Then you commit certain aspects of what you study to memory. These are things like definitions, particular conditions for certain things to happen, because again, if you understood what is happening, it's even easier to commit those to memory. Revise to make sure the understanding is solid. Okay, and then the next thing that you want to do is to exercise, meaning put it to practice. And then, of course, guys, the second thing you want to do is to not waste time on socials. Okay, if you really want to succeed, stay away from socials, especially when it's just all gossip and simply just trends. Those things are just useless, and they tend to attract your attention because your brain always loves to be relieved of being a participant. So please stay away from wasting time on socials and gossips. Those things are the most useless things you can do for your life, because guess what? Those kind of things are going to create difficulties for you. How? If you don't study well, you will not understand well. Even though you may pass matric, it still means you don't know much. You may not have a good job. You will be a slave to somebody and not live a good life. But if you do what I'm telling you, you will be the best, okay? Or among the best at least. And that means you're going to get a good job. Or you may even become an entrepreneur and actually identify job opportunities and start businesses and even become wealthier instead of just, being well off. And you know what? Then that is when you live a good life, because all the soft life you watch on TV and you see people faking, by the way, is something that not so many actually have. Even the many of which we think they have, they actually do not. I'm not being mean, I'm not hating, but that's just the reality, guys. Okay, don't waste time on socials. And then, of course, 3, eat healthily. Be careful. Most of the things that are told to you that they are healthy, like you must eat greens, they are healthy, you must eat lean meat, it's healthy. Well, you know what? That's not correct. Okay, not exactly correct. It's partly correct, but it's not exactly correct. Okay, eating healthily is just a balanced meal. Remember, for cells to replenish themselves, you need fats, right? So you can't say you will run away from fats. You want free fat. This, wada, that's just stupid. You still need fats, because fats help us to replenish cell membranes. Replenish cell membranes. And what is the utility of cell membranes? In neuronal cells, the cell membrane is the excitable tissue. This is how we transmit information from one area to another, actually using the cell membranes. Okay, so in neural cells, the cell membranes is the excitable tissue. Even in muscle cells as well. That's what gets the electric impulse, because these cell membranes, when you get to university, you learn that they have a bilipid layer. Okay, these are fatty acids and some what you call fatty acids and what again? Oh, I forgot these things, but anyway, you have something like that. So you have this series of these, bilipid layer. But now on the outside, you have, there's charges. Sometimes they are pushed outside and then sometimes they are inside. But on the inside, you tend to have more negatives. Okay, we can say this is the barrier of this bilipid layer, meaning that is the outside, that is the inside. You have negatives mostly on the inside, which is because of the proteins and, lipoproteins or polysaccharides, whatever you call them. And then on the outside, you may have positive charges, things like sodium and stuff. So when sodium gushes in through some special, special holes in the membrane that we call channels. So when these ones open under certain conditions, of course, if a membrane gets excited locally by nerve, it depolarizes. Sometimes that depolarization can change the conformation of that protein, allowing more sodium to gush in. Once it gushes in, you start to have a change of negatives to positives on the inside. This is when the muscle cell will contract or a nerve cell will transmit what we call an action potential, or a sort of like a nerve signal, so to speak. This can get propagated because of certain specializations of these tissues. So it goes distances. If you want to move your toe or to wiggle your fingers, you actually decide in the brain. But all of these things are sent via these pathways. But guess what? You're using cell membranes. It's cell membranes that are actually doing this. The rest of the fibers on the inside is just a scaffolding to create a pathway. It's like building the roads. But actually what is moving on the road is cars, isn't it? Yeah, bo. That is the story, guys. So you can't eliminate fats from food. And then you need carbs. Okay? Carbohydrates, they are the quickest form of energy. And you need energy to move signals distances. So carbs help you to propagate these signals. This is what gives you endurance, longevity, and also wakefulness, concentration, you name them, right? You need proteins. As you can already see here, this basic membrane here, there's a protein channel. So the channels are usually proteins, okay? So you need proteins to make sure these are working well and they are replaced. Again, proteins help us to create the scaffolding, to create new pathways or to replace old ones. So you see all the scaffoldings is basically proteins, usually collagen, type 1 or 2. You will see when you're doing biology at university, like serious stuff now, not this weak thing you do in matric. It's just the basics there. Okay, you need proteins. Again, these ones can be changed to carbohydrates for energy purposes. This is what we call gluconeogenesis, when you're creating glucose from other sources than just starches. We call it gluconeogenesis. This happens in the liver in the human body. So when you eat well, you don't drink alcohol, you don't smoke, you don't eat rubbish, what happens is your liver is going to be able to store enough of these and be able to convert these at will. And by the way, these ones, the proteins, give us a sustained energy supply. Carbs burn quickly, so they don't give you a sustained. This is why sometimes these energy drinks you drink are not so good, because they just give you an influx of high energy and then it's gone. Bam! It's like burning a paper, right? So that's not very good, because it gives you the feeling that you can go on, but you actually are exhausted. So it's not good, because as soon as it's gone, you've already even overly run some of the systems that are available. Therefore, it takes time to recover. That's why you crash and burn. So don't do those things, okay? But you understand what I mean. Even fats themselves can be converted to glucose. Again, they give you a bit of a sustained, but not as best as proteins, okay? So if you eat meat, you will notice that when you study for longer. You concentrate for longer than when you've eaten fats. Sometimes you get tired quickly and then you want to sleep. but carbs, they almost don't do anything when you're already tired. Okay, but they are the quickest things you can use while you are trying to convert this, because this conversion takes a bit of time. These ones are almost instant. So like I'm saying, balanced meals, you can't say you're not gonna take carbs, you can't say you're not gonna take fats, you can't say you're not gonna take proteins, but don't overly indulge on fats alone, don't overly indulge on carbs alone, don't overly indulge on proteins alone. And then of course, these positive ions I talked about in charges, it means you must be well hydrated, okay, meaning electrolytes. You guys are told, don't eat food with salt, you're gonna get hypertension. That's rubbish, because to even regulate your metabolism, even the blood pressure itself, you still need sodium, because it is neurally, regulated. And now if you don't have salt, you're going to have difficulty regulating that blood pressure. So you need salt, but not too much salt, because too much salt will retain too much fluid. Too much fluid will increase your hydrostatic pressure. That's when you get hypertension. And in fact, it only does that when you're already hypertensive. So it worsens it, rather than when you are not hypertensive and then all of a sudden you have hypertension. So that does not happen. It's not true. So you must be well hydrated. Take electrolytes, meaning salts must be in your food. Salt is important, but again, like I said, balanced proportions. You can't eliminate them. You take balanced proportions. All right. And then of course, guys, your food must be cooked. Okay, avoid eating raw foods. I know you believe in salads and all of those things. Those things are not healthy, guys. Believe me. Look at people who live that lifestyle, how many health issues they have. They are the doctors' people. We make money through those kinds of people. But the ones who cook their food, like boiling food instead of frying foods, those ones are the rural people. How often are they sick? How often do they lie in a hospital bed and not recover and require so much hospitalization? It's usually when someone is going to die. If they're the rural people, if they go to a hospital, usually you could expect that, because those people actually become better without even going to the hospital and drinking any medication. So anyway, guys, these are some of the things that I expect you guys to be able. And then of course, the last one, behave well. Okay, don't be hooligans. Don't be hooligans. Behave well, meaning do maintain your ambitiousness. Be ambitious, meaning aim very high, okay? But remain humble as well. Don't be naughty, don't be silly, don't be judgmental, don't be negative, don't be toxic. And then of course, have respect, both for self and others, okay? Be dedicated. Dedicated to your work. No, don't be dedicated to your friends and whatever. Okay, guys, I've said more than I was actually planning to do here, but I can tell you, if you combine these 5, that's a bullet that can shoot multiple times. In fact, you shoot once, it kind of rockets all around your targets until they are all down. So you don't have to fire again. If you have to fire, you just want to, make sure you're killing things instead of just hitting them this time around. Okay, guys, goodbye for now. I'll see you when I see you.